Okay, let's review for the exam. So that's going to be the first one. And it's a capacitor. It's an easy one. And it says isolated. So it means that the capacitor is not connected to the battery. Okay, and it's charged. So you have a charge Q that has to stay there, cannot go anywhere. And you have an electric field that has to stay the same as well, because for each plus here, you have a minus here. So the electric field and Q cannot change. However, the voltage here between the plates, yes, it can change if you change the area, for example, or you change the distance between the plate. Okay, so if you look at your equation here, for example, let's see, capacitance here, you have that by definition, the capacitance, you can use, you can play with those equations, but you see capacitance is by definition the charge per unit voltage, and it depends only on the geometry. Okay, so the capacitance is the geometry, so it depends on the geometry, inversely proportional to the distance. So I'm going to call that distance G. So that will be the distance between the plates, and it is given. So that's G. This is the area A, and that's going to be Q. That's G1, and that's going to be G2. So the capacitance is given by this equation, and it is by definition the amount of charge per unit voltage. Okay, so that will be the voltage. So you see that this has to stay the same, this stays the same, and D it's going to change. Okay, so delta V equals, so isolate delta V, it's going to be Q times D. So Q times D over A epsilon 0. And the D that I'm going to use is just going to be the D here. So this is TMI. It's too much. I mean, you don't need it, right? So all you have to do is plug in. Distance here, you have to be careful. It's 0.04, right? And then here, the area, it's going to be 0.4. It's going to be 8.85 times 10 to the negative 12. And you find the answer, which is 8 volts. So I'm skipping number 2 because it's easy. It's about the pointing vector, I think. So it's just plugging in. So this one is also easy, but you have to go in 2 steps. So you have a proton and you accelerate the proton. Okay, so maybe you're going to have a plus here, minus there. So there is a voltage applied here. So delta V, which is 1000 volts. You have a proton here, start with no speed, and it's going to accelerate here. Okay, so here it's going to accelerate because there is an electric field pulling on it, right? And then here it will keep the same speed. And let's say it's going to enter a magnetic field, which is uniform, so it means same magnetic field everywhere. Let's say it's inside the screen here. You take your right hand. Okay, you take your right hand and you see that the force will be, in that case, perpendicular to V, perpendicular to B. So in that case, it's going to be here. And we have a circular motion. Okay, circular motion. So it doesn't speed up, it's just F, the magnetic force here, will be like a centripetal force. Okay, so for that first step, you can say that the potential energy, so E delta V, okay, is going to turn into kinetic energy. So 1/2 m, and that's going to be the speed square. Right? And then, okay. So that will be for this. And for that phase here, we have the force, the magnetic force equals E VB, okay, because remember the magnetic force is QV cross B. Okay, you can check the QVB, it's a cross, so it means it's perpendicular. But here in that case, it's perpendicular, so we don't have to worry about any sign. So we have EVB, okay, so the magnetic force equals centripetal force, so M, and then the V square, and that will be the radius that we are trying to find. So cross. So you can cross this, cross that, and you have different way to do it, okay? So you have to play with those equations. You have equation 2 here, equation 1. So what I'm going to do, I'm going to take equation 2, but you can do it, you can find the speed here and plug the speed there. Maybe it will be easier, right? So you use that equation here and you isolate the speed. So you find the speed here, you take the square root, and then from here, you plug into there and you can find the radius. Or you can go only algebraically. That's what I'm going to do. So I'm going to do equation 2. You have the, let's say you have the speed equals E times B times R over M. That's from equation 2. And I'm going to plug that into equation 1. So I'm going to have E delta V equals 1/2. Here I have the mass and then have the speed square. So that will be from equation 2. That's equation 1. V square is going to be given here. So B square R square M square. So just to do it algebraically, but again, you don't have to do that. Okay, you can solve step by step. You can use equation 1, find the speed, and then you plug the speed here. So if you do that, you goes bye-bye here, and then you goes bye-bye here. You isolate R2, which is 2m delta V over E, and then you have a B square. Yes, so the radius, and I take the square root. So it's going to be square root of 2m delta V. E is the charge of a proton, and here you can take it out of the square root. So just to do a little bit of exercise here, but you don't have to do it this way. And so you see the radius is inversely proportional to B, okay, because if you have a large B, it will be more curved, right? And it depends on the mass. More inertia, larger will be the radius. It depends on the voltage and the charge, okay? And if you do that, you can plug it in, and I'll let you do that, and you should find, check, so 11 centimeters about. So I'm skipping one question again. So this is, actually it's very simple. So you have the pointing vector, okay? So the pointing vector is in the direction of the electromagnetic wave propagation, and it's a cross product, right? It's going to be 1 over mu 0 E cross B. But anyway, the idea here is that you have to use your right hand. So it means that if this is along the x-axis, this is along the y-axis, that will be along the z-axis. Or if this one is along the y, this one will be along the z, and this one will go along the x. So it means you take your right hand and you follow the right hand rule. Okay, so let's see what's going on. You have x, y, z. So I'm going to make a x, y. So y is here. X, Y, Z. According to the right hand. And it says E is along the negative Z. So that will be here E. And then B is along the plus Y axis. So that will be B. So then you take your right hand, the thumb is toward E, the second finger is toward B. So the third finger should be along the x-axis. So that will be the direction of the propagation of the electromagnetic wave, right? So if I just show you B, it's gonna go, the electromagnetic wave is gonna move in this direction. And B is gonna go up and down, and E is gonna go this way, perpendicular. So the answer is positive X. So this one is easy because you just have to be careful not to confuse voltage and electric field. Voltage, you use the superposition principle to find the voltage at a given point in space, right? So if you call that label the charges, you want to find the voltage at that point P. Okay, the voltage at the point P will be the voltage from V1, from 1, plus the voltage from 2, plus the voltage from 3, plus the voltage from 1, 2, 3, 4. And you see that the 1 and the 2, when you add them up, it's going to be 0, and this one is going to be 0, so it's going to be 0, because they are at the same distance. And what's the voltage? Is K times the source here over the distance R. So I'm skipping one more. I think I skip one more. So this one is not hard as long as you draw the situation. Okay, so you have one which is 10 amp, another one which is parallel here, and opposite direction which is 10 amps. So you have two parallel wires that carry, and they carry current. And the distance between them, it says it's 40 centimeters. Okay, so what's the magnitude of the magnetic field in the plane of the wire at a point which is 20 centimeters from one, 60 centimeters from the others? So first of all, remember that the magnetic field produced by a wire is this. Okay, it's in your equation sheet, so it's going to be mu 0, the current 2 pi r. So it's inversely proportional to the distance. And you can use your right hand. So instead of using this, I'm going to use this view here. So that current, I'm going to call that I1, and it's going into the board. Okay, so it's perpendicular to the board, and I'm going to call that I2, and the current is coming towards you. But the wires are perpendicular to the board. That distance here is 40 centimeters. And you want 20 centimeters. Okay, so it means that you want here let's say this is 20 centimeters. So you want, for example, at a point here, P, okay? So that point P is 20 centimeters from I2, 60 centimeters from I1. So you see that if you use your right hand, I1, so you make a circle, so you put your thumb into the blackboard and you go around with your hand. You see, it's going to make a magnetic field. The magnetic field always like to circulate here. It's going to make a circle around I1. Okay. So here the magnetic field B1 will be in this direction. So that will be B1. It's a vector, so it's tangent. Okay, you're gonna have a B1 here. You're gonna have a B1. You have a B1. And so forth and so on. And then this one, the current is going towards you. Okay, so it means it's gonna make also a magnetic field, but all around here, it's going to be the same magnetic field, but it's going to circulate here in the opposite direction. And no, it's going toward you. Sorry. So it's going to circulate in this direction. Okay, so the thumb is toward you and your hand is circulating around counterclockwise. So that's going to be your B, I'm going to call that B2. And you see that it's going to be stronger than B1 because the distance is smaller. Okay, so remember, each time you have a current I, it's going to produce a magnetic field here around that will circulate. At a distance R, the magnetic field will circulate. Circulate. And you use your right hand, and as you move away, it's gonna be weaker. Okay, so we have two vectors, but you see you have to subtract them. So you have mu0, I, and here you have 2 pi R1, and B2 in magnitude is going to be the same I, but now we have 2 pi R2. Okay, so B in magnitude will be B2 minus B1. Okay, so you can factor out that will be I, the current is 10, 2 pi, and then we have 1 over 0.2 minus 1 over 0.6. And I don't know why I divided here. It's a minus, right? It's going to be B2 minus B1. Okay, so you plug it in and you can simplify. Yes, you can simplify here because mu0 is 4 pi times 10 to the negative 7. And if you plug it in, the magnitude will be 6.7 times 10 to the negative 6 Tesla, which is micro. So as long as you do your diagram, it's not bad. So this one is just to remember the equation. So it's Faraday's law of induction. You see the MF is d phi over dt. So it's just to remember the equation. So the flux here of the magnetic field is given by 5t to the third plus 5. Yes. So the EMF induced is by definition d phi over dt. And don't worry about the negative, so that will be the magnitude, which is 15 t squared. So the EMF at t E equals 2 will be 15 times 4, which is 60 volts. So it's just a way to check if you know how to use your equations here. See, this is this equation there. Right. So this one is about the electric field, and we already did something like this. Let's see, it's 1 to 30 centimeter here. So you have a positive charge there, and you have a negative charge here. And they want to find the electric field here. So to find the electric field, imagine you have 1 coulomb of charge, which is positive. And let's call that number 1. So it's stronger, but it's farther away. And number 2 here, it's closer, but it's smaller charge. So this one is going to push this one. So we're going to have a E1 here. And this one is going to attract. So we're going to have a E2 there. Maybe stronger because it's closer and it depends on the distance square. So that would be E2. Okay. And then you have, by definition, so you need to add them up because they have the same direction. So it's going to be 9 times 10 to the 9. And then you have the source. And then you have 1 coulomb. And the distance here is 0.3 square. Okay, so you can do 45 times 10 to the 3. And you have a 0.3 square. And E2, it's going to be 9 times 10 to the 9. And then you have a 4 times 10 to the negative 6. And then 1. And then you have a 0.2 square, which is 36 times 10 to the 3 over 0.2 square. So you add them up. And if you add them up, you get something like 1.14 times 10 to the 6 Newton per coulomb. Okay, easy. Okay, so this one, I don't know. I don't think it's hard. It's just Gauss law that says the flux, the electric flux, okay, through a closed surface is equals to the charge inside the surface over epsilon 0. That's the electric flux. And the electric flux, if the electric field is the same all over the surface, okay, and it's perpendicular to the surface area, is just electric field times the surface area. Okay, so now you have a non-conducting sphere. So this is a sphere here. It's not conducting, so it's positively charged. But it's a continuous distribution, so all over inside the sphere. The density is given, which is the charge divided by the volume. The radius is 5 centimeters, and you want to find at a distance of 3 centimeters. So because of the symmetry, if we are at a distance 3 centimeters, okay, we can see that the electric field will be the same all over the surface here. Okay, it's going to diverge and it will be perpendicular. So this is an imaginary surface area, so imaginary closed area, and it's a sphere that I'm going to carve out of the large sphere. So that radius here is 3. And this one is 5. So the electric field, okay, So that will be the source, and the electric field here is going through, poking through this area. And the area is the area of a sphere. And the goal is to find here the electric field here at that distance there. And it's the same all over that surface. So I'm going to use that equation. So E times the area, this area here, which is a sphere, equals the charge inside. So that will be the size, the charge inside over epsilon 0. So the electric field times the area of a sphere is 4 pi r square equals the charge inside, so it will be the density times the volume, okay? The charge is density times the volume, and the volume here is a solid sphere, so it's 4 over 3, and it's a cube because it's a volume over epsilon 0. So you can say bye-bye to this, you can say bye-bye to that. Okay, you can say bye-bye to this. So you see that the electric field in magnitude will be rho r over epsilon 0, and there is a 3. And then you can plug it in. Okay, you can do 100 density micro 10 to the negative 6 times the small distance 0.03. And then you have a 3 times 8.5 times 10 to the negative 12. The unit will be Newton per Coulomb for the electric field. And you should get like something like 113,000 Newton per Coulomb. Okay, so this one is just for you to use the equation here again, the EMF induced when there is a change in the magnetic flux. Okay, so you have a coil here which is rectangular and it has 60 turns. Okay, so 60 turns. And the area is given, so that will be the area. That will be N. And somehow, don't ask me how, the magnetic field going through here is going from 0 to 1.4. So at t equals 0, there is none. And then it's going to increase magnetic field going through here. Okay, and then it's going to increase even more. So you have more lines here and even more. So it means that the change in magnetic field will be 1.4 minus 0, which is 1.4 Tesla. So the induced EMF is the number of turns and then delta phi over delta t, and the magnetic flux is by definition B times A, okay, because it's perpendicular, so we don't have to worry about the cosine. Okay, so delta phi over delta t, so in that case it's Faraday's law of induction, so delta phi over delta t is delta B over delta t. So the change in flux is because B is changing. So that will be delta B over delta t. So the EMF will be 60 times the area. So the area is 0.08 times 0.1 over okay, I think you can do it on your own. So the EMF will be 60 Okay, the number of turns times the area, which is 0.08 over 0.1, times the change in B, which is 1.4, over the time elapsed is 0.1. So that goes bye-bye. So EMF equals, you're going to have 60 times 0.08 times 1.4, and you get 6.72 volt induced. So you're going to have a current induced as well that will oppose the increase of the magnetic field. So you're going to have a current induced here. So this one is about motional EMF. So it's a EMF because the area here is changing. So someone is pulling, so it keeps that bar here moving at a constant velocity. So the length of the bar is given, and then the magnetic field here is in the board. Okay, so that will be your magnetic field here, B. The velocity here is given. The load here has a resistance R. And what's going to happen to the bar? So first of all, you can imagine that the charge carrier is positive here, which is not the case, but let's say it's positive. And so that's why it's easier to use the right hand rule. So V is to the right, B is inside the board. So the positive charges, they're gonna feel a force here. So they're gonna accumulate here, and that will be minus. So you're gonna develop here an EMF. It's like a battery, but instead of having chemical reaction here, it's because of that force on the positive charges. So here you're gonna have positive, and here you're gonna be negative. So it's like a small EMF. So now the current is gonna flow here. It can flow through the load. Okay, and it's gonna go this way against the electric field. Okay, so now remember that we have a force. A magnetic force will be ILB. So if you have a current inside a magnetic field, it will be acted upon by a force, and that's going to be the force. So again, you take the right hand rule. I is up, B is inside the board, so the magnetic force will be to the left. And it makes sense because it will oppose whatever gave rise to. So this is called Planck's law. Okay, it's going to try to slow it down because it's conservation of energy. Okay, so anyway, so that's going to be the force. Now we have the, what do we want? We want the magnetic force, but what is the current? Because we have L, we have B. So the current will be the EMF. Okay, so it's like a DC current divided by the resistance R. So what's the EMF? So the EMF is the change in magnetic field times area. And in that case, magnetic field is not changing. So the EMF will be B, the change in area over time. Okay, so if I call that, so that distance here is L, or L, or uppercase here, uppercase L, and that distance here is X. You see, X is changing with time. So you see that the area is L times X. So the EMF will be B, L, and then you have delta X over delta T, which is B, L times V. And actually, you don't need to derive all that because I think here, you see it's given. It's called the motional EMF because it's a typical problem. Okay? So anyway, so we go back. The current will be BLV over R. So the magnetic force will be the current, so BLV over R times L times B. So the magnetic force will be B squared L squared V over R. Okay, so make sure. Oh, you can do it step by step, right? So if you do LVB here, you're going to find 0.12 volt. The current here is going to be 2 amps. And if you do the force here, you should find 0.48 and the direction will be at left. Okay, make sure this is correct. So the current is the EMF, BLV over R, yes. So that will be BLV, that will be the current, okay, times L times B, B square, L square, VR, yes. Okay.
Je suis d'accord.
Okay, so this one is to apply Lenz's law. So when the magnet is toward, so it's falling. Here you have north and south. So what's going to happen here? It will the current here will flow in this direction. You can take your right hand such a way that it will behave like a bar magnet with a north here and a south here, trying to stop it, right? It doesn't want the magnetic field to increase, the flux to increase, the number of lines going through to increase. And then when it's passed, so now we have the south here and the north there. So the magnetic field is going to decrease. So it does not want that to decrease. It does not want the magnetic field to decrease. So it's going to flow in the opposite direction. So everything happens like it behaves like a ghost bar magnet with the north here and the south there. Okay, almost done. Okay, so this one is just the schematic that can be confusing. So what you can do, you start from here. So I'm going to do this, schematic here. So you start with the EMF, which is 12 volt. Okay. Up. You have a load here. So I'm going to put a load here. And then you have two paths. So I'm going to make two paths. So it means we're going to have two branches. And this is one branches, even though it makes like a corner, it's just one branches. Okay, because there is no intersection. So here we have an intersection. That's my intersection. So here you're going to have a 2R. And here you're going to have a R. And then there is no intersection. So I keep going. That will be in series, right? So then they combine together. We have an intersection here and goes to ground. So here we have a 12 volt and we have a R. So here we have 2R because it's in series. So 2R and 2R in parallel. That's going to be a R. So now we have a 6. So that's going to be 6 because this is 3 ohms. And that's going to be 3 ohms. So everything happened like you have a 6 ohm resistance. You can replace all this by a 6 ohm 6 ohms resistance, that will be equivalent resistance, so that has to be 2 amps. So we go back to here. So we have 2 amps from the battery, and then it's going to split, but equally, because you have the same resistance here. So that will be 1 amp, and that will be 1 amp. So if I want to find the power delivered, not delivered, consumed, so P equals R, which is 2R I squared. So that's going to be 6 times 1 square. That will be in watts. Okay, so we are almost done. So this is the EMF because the area is revolving. Okay, so we have a loop. Okay, so I don't know how to draw that, but you have a loop here, and this is your loop here, and it's rotating. And you have a magnetic field. So the magnetic field is not changing. Okay, so you have a magnetic field here, it's constant, B. But here, this is rotating. Okay, so this is a loop with 6 turns. Okay, so 1, 2, 3, 4, 5, 6. That will be your area vector. Okay, so between here and there, it's going to make an angle theta. Okay, so the number of, it's going to be 6 loops. The area does not change, 0.04 meters square. And the magnetic field is 0.2. And it's rotating at a rate of 50 cycles per second, or 50 hertz, or you can say 50 revolution per second. So you can, that's a speed, okay? So the rotation speed, okay, so how fast it's gonna spin is 2 pi, okay? So 1 revolution is 2 pi over the time for 1 revolution, which is the same thing as 2 pi times the frequency. Okay, frequency is 1 over the period. This is the time for 1 cycle. This is the number of cycles per second. That will be in rad per second. So it's like revolution per second, except I'm using, for 1 revolution, I'm using 2 pi. So the unit is rad, but it's really how fast it's going to spin. So at a given time, okay, that angle here, theta, that will be the angular displacement, is just the speed, so rotational speed, times the time. Okay, so it's like delta x equals vt. So that means the angular displacement, the angle swept after a time t. Okay, so what else? We need to find the EMF. So it's like a motional EMF again. So the EMF is by definition the number of loops, delta phi over delta t. Okay, and phi is B times A. But now we have the angle, we have a dot here, so it's the angle is theta. So that will be this angle there. So phi is B stays the same, A is gonna stay same, and here we have omega t. Okay, so it's gonna be n. So if I take d phi, so it should be a derivative here. I'm gonna take the derivative. So it's gonna be d derivative. It's gonna be ba cosine omega t over dt. So you just take the derivative of cosine, which should be sine. So we're not going to worry about the negative sign. And in the negative, you take the absolute value. So if you take the derivative, you take this out, first of all, so we go N, B, A, omega, sine omega t. So you see it's going to change with time. It's going to be a sine function. And this is what we want here. That will be called the EMF max. So at that point, you can plug it in. Okay, so it's going to be 6 times 0.04 times the area, which is B. No, B is 0.2. The area is 0.04 times omega. So omega is 2 pi times the frequency. And that will be the peak. It's going to be the peak. So you're going to make a EMF. So it's like a voltage, right? It's going to go up to a peak and it's going to oscillate. It's going to be a sine function. So I do not know if you have it here. No. So you can derive it or memorize it. Okay, so almost done. So this one is just to see if you know how to apply the cross product. So if you place a current, a wire, a current carrying wire, there will be inside the magnetic field, there is a magnetic force. And by definition, it's going to be this equation here, cross B. That means cross. It means that if the magnetic field is parallel to the current or parallel to the wire, there is no force. So force to be applied, you need a component of B perpendicular to the wire. So you can apply the definition of the cross product, or you can say magnitude will be, for example, the current, the length of the wire times B perpendicular to the wire. Okay, that's one way to do it. So you have a B, you have a current along the x-axis. So there is a current here. It's a length L. Okay, so the length is L, and you have a current I. Maybe here it's going to be so maybe here you have a power supply somewhere. It doesn't matter. So you have a current I, and you have a magnetic field. So that magnetic field has two components. It has the X component, so in this direction, and the Y component. So it does something like this. You see a vector has an X component and a Y component, and it's uniform. Okay, so it has a Y component and it has an X component. So this is B. That will be the perpendicular component, perpendicular to I. That will be the parallel component. So it's only this component that will act on I. And if you take your finger, okay, let's do also the X, Y, Z. So this is X, this is Y, and this is Z. So if you take your right hand, I is along X, B is down, so along the negative Y. So it means that the force will be into the blackboard. So it means along the negative Z. Okay, you use the right hand. Okay, so I know it's going to be a Z component, and it's going to be negative. So negative I, which is 15, L, which is 2, B, but it's only the perpendicular component, which is 40. We already have the negative here. And that's going to be 1200 Newton. So F equals minus 1200 Newton K hat, because negative Z. Now, another way to do it, you could have said, use your math. So I, L, and then you have I hat cross, and then you have a 30 I hat minus 40 J hat. Cross here will be 0, so F will be I, L minus 40. And I hat cos J hat is going to be K hat. Okay?